Columbia in applied math, doing some very interesting research on geophysical fluid dynamics with an advisor, Polvani. Very well-known work. And since then, he's had a number of positions, but as I said, most recently he's been at the University of London. He has a very broad range of interests from astrophysics to geophysical fluid dynamics to high-performance fluid computation, and also he has an interest in mathematics and topology. But I asked him today if he would tell us a little bit about his work on hot and cold Jupiters applying to exoplanets. Please welcome James.
Yeah. All right. Now I sound like Darth Vader. All right. So as Brad said, I'm going to talk a little bit about some possibly exotic things on both cold and hot Jupiters. These are storms, waves, vorticity, and by the way of those objects, variability, particularly in the atmosphere of those planets. All right. So a little bit of caveat. There is some math in here, but not much. It's just equations, and I'll try to explain whenever they appear, what they mean physically, and then summarize. So I labeled this object just in case you don't know what it is. All right. So you're looking at Jupiter. This is an old image from Voyager days. Right? And what I want you to focus on is this big, gigantic thing right in front of you called the Great Red Spot. Okay. So this is this thing. This is a hurricane. As you know, hurricanes been in the news, particularly these days, often. This is a gigantic one. This is roughly an ellipse with a 2-to-1 ratio. I mean, it's about 20,000 kilometers across by 10,000 kilometers thickness. So literally, you can fit about 2 Earths in the middle of this thing. And it's been around for as long as we had telescopes. Right? Galileo has seen this in the mid-17th century. And it's still around. It's a very coherent, long-lasting structure. It does change, but just a little bit. It tends to breathe, so it oscillates, and it drifts slowly towards the west over a long time. But basically, this guy, more or less the way it's been looking like this for, almost 400 years now. Okay. So I start my talk with this object. At least in my field, the way we start this is with equations. This is a famous equation, at least if you're studying atmospheric dynamics or geophysical fluid dynamics. It's called the primitive equation because this is basically the equation that's the starting point for all of us. And it's basically Navier-Stokes or hydrodynamics equation with slight bit of augmentation. First of all, it's in spherical geometry. If you want to study global aspects, you can reduce it down to something that describes our Cartesian geometry. But I have to switch to two things. The important thing to note is that the equations are nonlinear, as you can see from this term, and it's for a rotating environment. And this set of equation is written from the point of view of the rotating reference frame. And it's compressible for a compressible fluid. And this last equation, this thing is called the hydrostatic balance equation. And the important thing about that particular equation is that the whole set of equation is meant to apply to large-scale flow structures. Okay? So large scale means just sort of a sizable fraction of the planetary radius, but not small scale features. Okay? Those involve full convection, and these equations doesn't really describe convective motions. That's something you need to parameterize in. Okay? And our basic approach is to just take this set of equations for which no general solutions are known. I mean, if you did know that, you'd get the $1 million Clay Prize immediately and go on to big glory. So generally, you're limited to trying to solve the equation numerically or simplify or reduce the set of equations down to something more manageable and try to see if you can attack it analytically. Yes?
Could you just help me with a few of the variables in there?
Sure.
So I don't know what K is, and FB and DB and FA.
Okay, great. All right, so V is the lateral winds. Okay, that's the velocity of the fluid at each point. W is the vertical velocity. So this is just decomposed into horizontal and vertical component. This is P is for pressure, rho is for density. K is the local vertical direction. Okay, F is the Coriolis parameter, or the effective Coriolis acceleration for a structure in spherical geometry. Right, so it's just written as F, but it's actually latitudinally dependent. Okay, so it's 2 times the rotation rate of the planet times the sine of the latitude. Sorry, it's lots of things are hidden in here. F stands for forcing. So this is the momentum equation. It's just the F equals ma equation for a fluid. So that's external forcing, and D is for dissipation. Okay. All right. Is it okay? All right. So let me just make one more caveat statement, and that's although these are the actual set of equations to do weather prediction for the Earth, for example, that's not really our goal. Well, we're not trying to precisely predict weather on other planets. It's hard enough to do that for the Earth, where we have lots of information available. We are trying to basically understand basic physical mechanisms rather than trying to make specific predictions. We're not there yet, and we're not going to be there for a long while. All right. So this is a close-up of the beast, the animal that we started with, the red spot. And I want to direct your attention to several things. First of all, this in our language is a vortex that's called an anticyclone. It's an anticyclone because the direction of the flow is opposite of the direction of the background rotation, which goes this way. So the background rotation vector points inward into the screen, and the flow is pointing out of the screen, right? The vorticity of the flow, right? Rotation of the flow. The other feature I want you to focus on are these wavy structures. And it's nice that Jupiter is so photogenic, and it has all these cloud features that literally track the flow for you, right? So it's very easy to see what the fluid is doing on Jupiter. And one of the things that's easy to see are these undulations, which are manifestation of something called Rossby waves, or planetary waves. These waves on the Earth are what's responsible for our weather, okay? Note also that this hurricane is embedded. It's sitting in between an adverse shear flow. So that side is going this way, this side is going that way. And while this thing is rotating, it's taking some of the material and actually folding it in, okay, creating this turbulent area. Note also that the vortex, although right here looks very elliptical, the true shape is more like a cat's eye. Okay? And one more final thing, if you squint really hard and look in the core of the red spot, although it's more visible in Galileo images, this is a Voyager image, there's a slight counter rotation in the core, in the middle. Okay? You have to squint really hard to see that one. But it's there. This is the red spot.
No, what is the white spot?
Oh, this is another vortex that's going completely across. And if you look at the movie that I've shown, this interacts very little with that one, and it just goes right across. Okay, but that's another giant spot. In fact, this thing, Jupiter, our cold Jupiter, has many, many spots, vortices on the planet. Okay, so those are the 4 things I want to concentrate on, because in the early days of flow modeling of planetary atmospheres, these things were modeled essentially as just an elliptical patch of vorticity, and you study things like, well, if I put another vortex nearby or underneath, would it coalesce or not? And that was sort of the state of the art as of, say, up until late 80s, okay? Before then, we had no idea what the heck these things were because we couldn't resolve them, right? Now, if you recall the primitive equation, if I make certain assumptions, I can actually write the whole set of the 5 equations into basically one equation for Q, this strange object called Q. And this is great because basically the equation I'm trying to solve is dq dt equals 0. Now this operator is defined like this, and you saw this equation in the original primitive equation. And what's great is that whenever you can write down a fluid equation that has big D blah dt equals 0, you are in business, because that equation tells you whatever that variable stands for, that Q stands for, it just acts like a tracer of the flow, right? So if you can identify Q in your equation and you plot that variable, it'll literally tell you what the fluid is doing at that instant. Okay, no other variable does that. And unfortunately, I made it, I'm talking very glibly, and made it sound like, oh, it's so easy to identify what this Q is, but actually it takes a bit of work, and the Q turns out to be this crazy set of terms, okay? Where this is a stream function, F is the Coriolis parameter that I mentioned, and this thing, the N is the so-called buoyancy frequency. So the atmosphere we're talking about is a stably stratified, non-convecting atmosphere. And this C is just a boundary term, okay? So what never mind what this is, the main point is that dq dt equals 0. And this is great, all right? It turns out Q is like a generalized vorticity, okay? This is already vorticity, but then these things added make it a generalized vorticity. And so we can model the red spot simply like this. The red spot is so you're looking at the flow field, a three-dimensional calculation simulation. You're looking down from the top, and you're modeling the red spot as an elliptical vortex column. It's uniform vorticity, right? Very simple. We're trying to make it as simple as possible, right? And these lines correspond to the external flow, the shear that I mentioned before. And they look like lines because that's what the flow looks like in vorticity space, okay? So straight lines connote east-west jet streams. And whenever there are tight gradients in the y direction of those vortex lines, that means an eastward jet. When there is relaxed gradient, it means westward jet. Okay? So far, so good? All right. The only sort of parameter that you need in this model is the unknown information about the vertical structure of the red spot. Now, remember, all we get, all the information we get about red spot is really from pictures, from images. At the cloud deck, we have no idea what's going on underneath. We cannot see past the cloud deck, right? How thick is the cloud deck, for example? How deep does the red spot go in Jupiter? So here, what we're doing is we're doing an inverse problem where we assume that the flow is describable by the equation that I just showed, which has one parameter that has to do with the stratification or depth information. Okay, that parameter, we'll call it LD. It's called the deformation scale, and this scale is going to come up at least several times in the talk. So let me write it down. Deformation scale plays two roles. One, it gives you an idea of what the vertical structure, stratification structure is. It also plays the role of the interaction length between any two flow structures that's in your field. Okay? For people who do plasma physics, it's kind of like the Debye length, if you want to think about it that way. Or people who do particle physics, maybe like a Yukawa potential. Okay, something whose interaction length kind of falls off with certain distance. Okay. All right. So the inverse problem is this: if I initialize my calculation as I just showed with the vortex column, with the background adverse stream, and I only have that one parameter, the deformation radius, to play with, I'm going to now vary that parameter and then try to match up with the features that I pointed out on the red spot. Right? How close can I get with this algorithm? So here's a case with the deformation radius of 4,000 kilometers. Okay? It turns out that the 4,000 kilometer length scale is too big. In other words, the interaction between the vortex and the jet stream that it sits on is too strong, so that the vortex, the red spot, is actually taking the flow north of it and wrapping it around, and it's unstable. Okay? So that's no good. So we know that the deformation radius is not that value. Let me go the other direction and use what I would consider a very low value, 1,000 kilometers. Okay? And then you get this thing. So why is this thing happening? Well, here the deformation scale is too small. Okay? When it's too small, you can imagine that one side of the red spot does not know that the other side is part of the same entity. Right? It loses its coherence. And therefore, eventually the whole thing falls apart and just homogenizes the vorticity in that region. And this is what you see. If I kept on going, eventually all you see would be just straight lines. So that's no good also. Now the Goldilocks value. This is 2,000 kilometers. And it turns out, subsequent to this study, people have obtained other independent measures, and this turns out to be about the right value. Okay, 2,000 kilometers. And there, look what's happening. You get all of the features that I just pointed out. First of all, you get this cat's eye looking vortex, right? You get the wavy Rossby waves to the northeast of the vortex. You get turbulent region from that flow being folded down. You also get, it turns out most of the action of the red spot happens in this collar. And that width of the collar is about 2,000 kilometers. That's not a coincidence. It's because of the equation and how the deformation scale goes into the equation. Okay? And because of that, there is a very weak counter-rotation in the core. So it captures everything that you would like to see. I'm not saying, this is perfect, but this is pretty good, especially considering it's such a simple model. Okay? So just for comparison, you can see for yourself, right? Remember the 4 features that I pointed out. Yes?
What kind of lines are there? In a laboratory experiment, you're watching the iso concentration lines. What are those lines?
On the right-hand side or the left-hand side? Both. Good. Okay. So this is material lines. So they're kind of like concentrations. These are cloud. The closest thing to that for theory is the vorticity, or more precisely, potential vorticity, because all of these material would just simply follow the contour lines of it.
What are the lines on the left?
This is the potential vorticity, the vorticity contours, right? Okay, so it's the curl of the velocity added with the other terms that I showed 2 slides ago. Is that okay? All right. Okay. Now, this is a study that was done, now almost 20 years ago. Okay? So here's something, something stupid that we realized after we actually did the calculation. The algorithm was so good that when we came to print out the result, it turns out no printer at that time could actually print out the result. So we had to actually degrade the image in order to put it down and publish the results, right? Now, 20 years later, we don't have such limitation. And typically you get calculations like this using the same algorithm. This is done on done on my laptop. And already it's many orders of magnitude, better resolution than 20 years ago. But using, again, same algorithm. Okay. Another thing I want to mention is that Jupiter, and also to Saturn to a lesser extent, and even Uranus and Neptune, so the icy giants, there is an interesting feature about the storms, the many storms that you see on all of these planets. Jupiter is the best example of this. When you take a census of the chirality, the handedness of the storms, it turns out over 90% of those are of the anticyclonic kind. Okay? So in the northern hemisphere, remember the planet is rotating this way, so the anticyclones are pointing toward bottom or pointing out, right? And then it reverses sign in the southern hemisphere. But, so this is an observation. Voyager and Galileo went there and took a census of all the vortices, and we were surprised to find out that almost all of them are anticyclones. Okay? There are few cyclones, co-rotating vortices, but they tend to be very small and weak. Why is that? And it turns out Saturn, though it's harder to see because it's more hazy on the Saturn, it exhibits the same feature. Okay? Well, that's also easy to see. We start from the primitive equation again, and we just vertically integrate because we're not interested in the vertical information. And by reducing the problem down one dimension, I can do a lot more high-resolution simulations or numerical studies. And so I did that. I vertically averaged the equations. And in the end, you get something that is very well known in geophysical fluid dynamics, a set of equations called the shallow water equation. Okay? This equation describes a thin layer of fluid, right, which is homogeneous density, that evolves under only gravity, okay, gravitational force, and rotation, and that's it. Okay. Okay. Now, if you scale and look for symmetry in the equation, it turns out that it turns out that let me try and explain this. It turns out if you try to do a randomly initialized, very turbulent, in other words, high Reynolds number calculation, like Jupiter is. In other words, you start a simulation where you just kind of randomly stir the fluid and you let it go, right? The equation only has the physical parameters of the Jupiter's radius, Jupiter's length of day, rotation rate, and the thickness of the fluid. These are all things you can look up, perfectly observed values. When you do that, the flow goes turbulent, and it starts to undergo successive mergers. This is looking at vorticity from top down, and you see these vortices are continuously coming together to become bigger and bigger, and that is signified by something called the inverse cascade in the energy spectra. So the energy kind of goes up that way, which is completely opposite of normal turbulence you might have learned about, in undergraduate or graduate school, namely 3D turbulence, in which the energy always goes to smaller and smaller and smaller scale until at the end it's so small that the dissipation just wipes it out, right? In a fast rotating, density stratified environment, the energy doesn't do that. It actually goes the other way to larger and larger scales, okay? So while it's doing that, it does not look at cyclone-cyclone mergers and anticyclone mergers the same way. Okay? I don't want to go into too much detail, but basically the physics is anticyclones correspond to locally a thicker portion of the fluid. Cyclone corresponds to locally a depression in the fluid. And the way the deformation scale is defined, it's defined as it's proportional to the square root of the thickness, the local thickness of the fluid. So the anticyclones have greater or larger deformation scale compared to the cyclones. So they're able to merge more efficiently. They become stronger, and they can withstand any sort of external perturbation, whereas cyclones are less able to do that. And that's the origin of this cyclone-anticyclone symmetry breaking. Okay? It's due to the fact that the fluid can sense differences in the local layer thickness depending on whether you're a cyclone or an anticyclone. Okay? You can see this from, this is a PDF of vorticity, and anticyclones are negative. So, anticyclonicity is negative, cyclonicity is positive, and it's definitely negative skewed, right? If you look at the parameter space of the shallow water equation, this is a plot of so-called the Rossby number, which is a measure of the rotation rate of the hurricane or the vortex compared to the background rotation, and the fluid number, which is the compressibility of the fluid. Anytime you're in this region where the x's are, you'll see symmetry breaking. Anytime you're out of that region, that boundary layer region in the parameter space, the symmetry is preserved between cyclones and anticyclones. And of course, Jupiter sits squarely in this boundary layer. Okay? All right, so let me go on to sort of the next interesting aspect of planetary atmosphere, and there's waves. Okay, it said that like if you really wanted to characterize any flow, first thing you really want to understand is the vorticity, the spinness of the fluid, and then the second thing is waves. Okay. So you're talking about vorticity and divergence of the flow. Divergence is the divergence of the flow field that I'm talking about. Okay. Why is this important to study? Well, it's known, it's very well known, in fact, from many studies of the Earth, that waves that propagate from somewhere else will travel a long distance and will modify not only the flow, but the temperature at some other faraway distance. Okay? In fact, there are clear examples of on the Earth where flow goes over topography, over mountain on the Earth, and while the flow goes humping over the mountain, because the atmosphere is stratified, it kind of propagates, vertically propagating waves upward, right? We know in the stratosphere, there exists a polar vortex at high latitude. So my North Pole is over here, I guess. Right? And here's the topography. So the flow goes over, and it generates these upwardly propagating waves, which go up, and boom, boom, hits the boundary of the polar vortex. Sometimes these waves are energetic enough that it can actually destroy, or at least destroy part of the vortex, and that's how sometimes you get ozone hole opening up. So there's a very mechanistic explanation for why ozone holes occur and with why the frequency they occur. Okay, so that happens, Another sort of very technical thing that happens is as the wave propagates, it propagates with a particular phase speed. And of course, unlike the waves that you might have learned about in undergraduate school, waves almost always propagate through a medium that has inhomogeneities. For example, maybe the medium itself is flowing. Yep. And that's what their atmosphere is like. So if the propagating wave encounters a location where the flow speed is exactly same as the phase speed of the wave, we call that a critical layer or a critical level. It's a type of resonance. And I'll show you how that comes about mathematically. But when that resonance occurs, the waves saturate, and that's where typically turbulence would occur. Okay. Even if none of those things happen, as the wave propagates through, it's going to make the atmosphere slosh back and forth, and it creates lots of variability. Right? So there are lots of mechanisms, particularly on the Earth, and even on Jupiter, that we now understand very well that has to do with the, that originates from these waves and wave propagation. In fact, here's an example. You're looking at actually an image seen from DMSP. That's a military's weather satellite. Looking down, actually, you're looking down this way. This width is about 1,000 kilometers, and you're seeing waves that came up from below, and it's breaking in the ionosphere. Right? The clear signatures, and you see the ion signatures of turbulence. Very beautiful example. All right. We again start from the primitive equation, do some algebra, and write down an equation that, remember W is the vertical velocity, and this is a Fourier transform version of it. But basically, what you end up with is a very complicated harmonic oscillator or Schrodinger equation with a crazy potential. That's all it comes down to, right? This crazy potential is really what's interesting about this, though. The reason why it's crazy is because it's got all kinds of singularities lurking in there. So C is the phase speed, U is the background flow speed. Recall, I said that when they match, right, you have resonances. And this is where the singular points are. In fact, this guy is really nasty because it's second order singular. Right? Lots of different waves exist on planetary atmosphere, and almost all of them have this behavior in one shape or another. Okay? So we have to understand things like this very well if your final intent is to figure out what the general circulation, the general flow, and the temperature structure of the atmosphere is going to be like. Okay? I won't go through the other terms, but basically this is having to do with buoyancy, convection. This thing actually allows for convection. We need that because what happens, a typical example is, let's say deep down, the atmosphere is convective. This is true whether it's Jupiter or Earth or hot Jupiter. Deep down, there's some convection going on, and it's pumping up the air that's immediately lying above the convection area, right? This region of the atmosphere is very strongly stratified. So when you hit it like this, you generate and propagate up gravity waves, or all sorts of different kinds of waves. Yep. Now, the waves generally try to conserve kinetic energy, right? 1/2 mv squared, or 1/2 mw squared in this case. But the waves are propagating in a medium where the density, the mass, is decreasing exponentially fast upward, right? So if you want to conserve kinetic energy, the velocity has to grow and exponentially fast in order to keep the kinetic energy constant, right? So here's what it's doing. It starts off as a little tiny jiggle. It doesn't matter how tiny it is. As long as there's lots of room above it, it comes up and it does that, right? If it gets too big, it will buckle under its own weight, so to speak, and that's where the turbulence is occurring, okay? I will briefly show in a few slides. Earth, this definitely happens, and it's very important. For example, on the ground, the warmest spot on the Earth is at the equator. Coldest spot is at the pole because it's getting less sunlight at the pole, most at the tropics, right, at the equator. But if you go up a little bit in the middle atmosphere, it turns out the warmest spot is at the poles. It's reversed. The coldest spot is at the equator. And the reason is these waves come up, and of course down here the amplitude is very small, but up here the amplitude is very large. It goes toward the poles because the index of refraction for the waves is changing in the atmosphere as the waves propagate up. It goes toward the poles, and it's actually depositing lots of angular momentum and heat energy at the poles. And that mechanism is now well understood and well believed. Okay. It turns out, this is a picture of Jupiter at the cloud deck, and just underneath the cloud deck, you can see these gravity waves propagating. Okay, this is Io, the moon of Jupiter. It's not my hand or anything, or my thumb. Okay, so you can kind of get a rough estimate of what the size might be. Anyway, so these waves exist even on Jupiter, and if you're clever enough, not that I'm clever enough, but if one is clever enough, recall this equation. It's basically a fancy harmonic oscillator equation with this crazy frequency. But on Jupiter, it turns out that you can know this, you can know this. You can, well, these are small. You can know this, and that you can get from that image. If you do that, and this is also well known, you can invert the problem and figure out what C minus U is, okay? We can get the C from the image again, which is the phase speed, and that means you can get the flow speed, okay? It's using waves as a diagnostic to back out what the medium's information is. This is very similar to what helioseismologists do, but with pressure waves, with P modes, to look to measure the internal rotation rate of the sun, right? We can do that now for Jupiter, and the information that we use is information that was collected by the Galileo probe as it went down, as it fell into Jupiter. But luckily, lucky for us, it's unlucky for everybody who wanted to use the probe to probe a nice area. For us, actually, it did fall into a really nice area because where it fell in was a spot right near the equator. For a lot of people, they didn't want that because it fell into a very unusually dry spot. And they were hoping, the probe dropped into a more sort of usual area. But why this is important is that the only way to get information above the cloud deck, right, is by doing some sort of inversion of the flow that you see. Okay, then you can get the temperature structure. But that technique is absolutely no good for the equatorial region, for the tropics. And this is the only way you can get that information. And so we did that. What you're seeing on the right is a so-called Larm-Scargo periodogram. Okay, basically it's a Fourier power spectrum as a function of height. And look at the range of height you can get because the probe started dropping from way up high. So this is the first time you can get such a big range. Right? Before you were limited to distance about from here to about there. Okay? And not for the region near the equator. But here you can do that. What you're looking at is you're tracing the ray, and the ray is where the maximum energy is. And in fact, you can see sometimes the wave actually breaks, and it goes through a secondary propagation. It breaks again and goes. Okay? What's remarkable about this thing is before this work was done, there was lots of controversy about where the turbopause is located on Jupiter. The turbopause is the region where the main atmosphere is separated from the upper atmosphere. Okay, so chemists during chemical modeling put the turbopause at about here, and radiative to transfer people put the turbopause about right here, and this work confirms or suggests that the radiative to transfer modelers are correct by putting the turbopause up there. Okay, let me quickly get into the exoplanets because we're quickly running out of time. I don't think I need to say too much about exoplanets. You know, there are lots of them around now. You know, there are thousands. In fact, I stopped counting at 36. We don't, you know, it's enough. The interesting thing really about, from the dynamics point of view, about these exoplanets are that many of them, about a quarter of them, a fifth to quarter of them, are very close to its host star. Okay? When it's in that configuration, we think the orbit is in spin-orbit synchronization, like the moon is. Okay? So that it's rotating exactly once per orbit. Okay? The gist of that configuration is that the planet is always looking at the star as it goes around its orbit. So only the same place is getting you know, irradiated by the star throughout its orbit. So that's a condition nothing like we have in the solar system. The closest one is Venus, but Venus is not quite tidally locked. It's about 6 days off tidal locking, and that makes a difference. Okay, you might think it's small, but it's got a long time to work on Venus, and so even a 6-day difference makes a real difference. Okay. So there, you're looking at typical temperature profile from simulation, and we're looking at you know, gravity wave propagation on hot Jupiters, and there are critical layers, at least for this profile, that exist. Here's the acceleration rate. So it's actually decelerating. It's negative, decelerating the flow at that point. Okay? Great. That's no big deal. But here's the kicker. The kicker is that when the planet is so hot, right? Remember, the equilibrium temperature on this planet is like 1,500, 2,000 degrees. the temperature is associated with the thickness, the puffing up of the atmosphere, right? And recall what I said. These waves, the upwardly propagating waves, with the way they work, is the more room it has to grow, the more nasty damage it can do to the atmosphere, right? So on hot Jupiters, it's having a crazy effect on the background flow. Okay, very, very strong effect. Here, when there's no sort of critical layer or a very strong one, it's a little bit leaky, so the waves go up. If you started from say 1 bar location, it encounters the critical layer, and then it's a little bit leaky. So we're looking at maybe 50-degree heating and cooling, right, at that location, at that height in the atmosphere, okay, per 1 rotation of the planet, so per year of the planet. It's significant, but it's not great. However, if you start from where the convective region should be way below for hot Jupiters, now the effect is humongous, right? So we're looking at, effectively 1,000-degree changes, per orbit. So it really could affect the temperature, not only distribution, but variability, right? Temporal variability. Okay. Just to quickly show you, our further analysis show, like if you use those typical kind of profile, what you wind up with is a quasi-waveguide in the atmosphere. So there's where the waves will start, and there's some location where the wave experiences internal reflection, okay? So if you start a wave like this on the day side, and you might think, gee, if the planet is only getting heated on one side, does that mean the other side, even if the fluid doesn't move, will it always be cold? And the answer is no, because you can always excite these waves, and these waves, through the waveguide, will actually travel longitudinally and wind up on the night side. Okay, so there's a substantial amount of heating that way. So it's not just the flow, but also the waves that can heat and redistribute the heating. I'm going to slowly start to close down, I think, conclude. This is a picture I often show, but I show it in a slightly different context. Here, I want to tell you about another type of upwardly propagating wave, not gravity, but Rossby waves. These planetaries can also propagate up. And remember, in the Earth context, those are the waves that perturb the ozone hole very heavily. Okay, what you're looking at is a hot Jupiter, and it's the vorticity field again, so that you can see what the fluid is doing exactly. This is a side view from the night side, and this is view from the top. And what I want to focus your attention on is this feature right here. This occurs because there is not a physical mountain, but a thermal mountain at the underneath, deep inside Jupiter, because as you recall, when the atmosphere gets heated, it puffs up, right? And the puffing up is especially accentuated where the heat is being absorbed. And on the night side, it's like a negative mountain, right? It constricts. So if there's a flow going over, not only flow going over a mountain produces waves, flow going over a ditch also produces waves. And those waves come up and boom, hits the boundary of the polar vortex that exists on hot Jupiter. And this is what it typically does. This is a minor perturbation. It just kills the boundary. Lots of vortices that form due to instability. Okay, if it's very strong, it actually knocks vortex off of its center, right? And when it's in this configuration, the flow actually, because the flow is intimately tied with the vortex and the temperature distribution, it actually reverses, okay? And that also happens on the Earth. We call that sudden stratospheric warming. Okay? So same mechanism happens. So I guess one of the points I want to make here is, if you understand Earth dynamics, you can bring it in to explain lots of the feature on exoplanet as well as solar system planet. Let me just because we're getting close to the. So let me start to conclude. Okay, so I repeat again. I'm not trying to say I can predict everything. That I have no idea. Nobody knows. None of these planets are resolved. However, what makes these problems very interesting study, especially from a theory point of view, is we're in a dynamical regime that's completely different than any of the solar system planets that we know of. Theory hasn't been developed for these sorts of situations. So from that point of view, it's a great, interesting thing to study. For observers, I would like to emphasize once again that, sure, you could have very high-speed jets on these planets. However, as I hope I demonstrated, that there's sure to be waves on these planets. Waves are very easy to excite in planetary atmospheres, and they heavily modify these jets. Problem is, most of the current simulations do not account for these waves. They're simply too costly to put in unless you have a very, very good algorithm. Okay, so I throw a caution there once. I already pointed out that, sure, even without flows, the night side can easily be heated because they're ducting regions, and the waves can be ducted to heat regions that are very far from where the wave was originally sourced. Okay, this action in geophysical fluid dynamics is called teleconnection. That's the name that's given for this phenomena. And even if the waves don't make permanent modification, it's still important because observers only see or observe the planet at specific epochs, right? So it's important because it induces variability with a certain time scale. What I didn't have time to discuss today are other important factors, but these really should be included. For example, if the Jupiter is very close to its host star, and if it has normal solar content of alkalides, calcium, potassium, what did the third one? Calcium, potassium, no, lithium, no, not lithium. But anyway, the alkali, sodium, sorry. Sodium, they have very low ionization potential compared to hydrogen or helium. So, and you're in an environment which is effectively 10,000 times getting more EUV and XUV flux than, say the Earth is, right? And Jupiter is even further away, which means that the ionosphere is very strong on the Jupiters. And by strong, I mean it can extend very far down, right? So you need to account for ionization effect in your fluids. And of course, this is always a red herring in fluid dynamics. We're constantly trying to, do the best job we can with nonlinearity. And, question whether or not high-speed jets exist is still an open question, even though maybe sometimes you might hear otherwise. So with that, I'll conclude, and yeah, I think that's good enough. Okay, I'll let you read the summary, and thank you.
So, James, I sort of didn't get a feeling how important is Coriolis in this. So, for slow rotating planets, would Vorticity be in general smaller, or there's no significant dependence on that?
Oh, that's a fantastic question. Okay, so let me first talk about the specific and then more general, answer your question more generally. So for hot Jupiters, especially like the prototypical hot Jupiter like HD 209 458b, the effective rotation is somewhere in the middle. Like it's not very strong, but it's not negligible either. And that's a terribly interesting position to be in, right? So technically we say the Rossby number, which for say like Earth and Jupiter is very small. It's smaller than 0.1, meaning it's very like background rotationally dominated. For these hot Jupiters, it's order 1, right? So, but it's not 100 like Venus is. But now having said that, look at Venus, right? It's got Rossby number that's very high, so naively you might think, oh, rotation's not that important. But as I said, it's got a really long time to work on the flow. So in that case, eventually the rotational effect will catch up and modify the flow. So as I said, even though Venus is only 6 days or so away from tidal locking, if you look at the flow, it's it's zonal. It's mostly east-west. I hope that answered your question.
So you mentioned the deformation length and its connection to the red spot. Juno has been flying close to the red spot recently, or it's about to. Do you know if we'll get some information about the structure at depth?
Well, it's of course one of the stated goals. I think, in my opinion, it'll kind of do a marginal. It will answer that question marginally, because it can see undulations produced by flow at the bottom at the level of say like 5 or 6 undulations. But of course, if you look at Jupiter and see the jet pattern, there are at least something like 15 jets. So those are all undulations. So if they happen to go straight down, deeper down, Juno wouldn't be able to see it. Right.
Any other questions? Okay, let's thank James again.
Thank you.